Hello, and welcome to the Data Science Institute's virtual seminar series. My name is Dr. Leno da Silva, and I'm a data science ambassador at the Lawrence Livermore National Laboratory. Data science is essential to many of the lab's key program areas. With the help of some of the world's most advanced supercomputers, we work in a variety of fields and application domains. Through basic and applied research, our data scientists are working to solve some of the world's most pressing challenges, in areas ranging from precision medicine and advanced manufacturing to energy and national security. Here at the lab, the Data Science Institute acts as a hub for data science activities, including this seminar series and other events to introduce new ideas and encourage collaboration. Speakers from other institutions are invited to share their innovative approaches with our data science community. With recordings of these seminars, like the one you are about to watch, we are reaching a wider audience than ever before. So, welcome! If you have questions or want to follow up after the presentation, check us out online at data-science.llnl.gov or send us an email at dsi-seminars@llnl.gov. Now, sit back, relax, and enjoy the seminar. So let me introduce our speaker, Sean Newsam. He is a professor founding faculty at the University of California, Merced. He did a postdoc here at the lab in the past at CASC. So a very good person to reach out and propose projects and work with because he already knows how the lab works. He has been a recipient of DOE Early Career Scientist and Engineer Award, NSF Faculty Early Career Development Award, and a U.S. Office of Science and Technology Policy Presidential Early Career Award for Scientists and Engineers. His research interests include computer vision, machine learning, particularly applied to geographic data. So I'm gonna hand the stage to the speaker now. Thank you all for coming and enjoy.
Okay, hi everyone. I'm assuming you can hear me. If not, let us know somehow.
Just a note that I forgot. The talk is going to be recorded, so if you make a verbal question or if you turn on your camera, you're going to be recorded, so have this in mind if you don't wish to have your voice or image recorded. Thank you.
Great. Well, thanks everyone for joining, and thanks, Leno, for inviting me here. It's good to be back at the lab after a good many years. Let me get my slides going here. Okay, so I just a little quick slide on UC Merced and kind of relates to me and my time here at the lab. So I did a postdoc here ending in about 2005, at which time I went and joined UC Merced. And at that time, you can see this was kind of the state of the campus. This is a little bit before I joined, but by the time I joined, we had one building operational. This picture shows no buildings operational. And so we started with about 900 students and 55 faculty. I was the first CSE faculty. I was one of those first founding faculty. So fast forward almost 20 years, we're now 9,000 students, 450 faculty, and I actually wasn't able to find a aerial view that encompasses the entire campus. We've grown so much. Anyway, so a little bit of context there about UC Merced. So I guess my day job of the last 19 years has been building a university. On the side, I've been doing some research. So I have to kind of preface that it's been a good ride, but I haven't necessarily had the time to work on types of things that a faculty would at an established university. Okay, so quick outline of my talk. What is GeoAI and what should we care? Some themes of my GeoAI work. I kind of looked back over my work over the last 20 or so years, 25 years, and managed to find a couple of themes. And I'll then kind of introduce the themes, talk about some projects related to those themes. I'm going to go through these projects very quickly at a very high level, right? So there's not going to be a lot of technical detail in my talk. I'll refer you to papers if you want, but my talk is going to be at a very, very high level. And then I'll transition to the present, which will be current work, not my work, other people's work on foundation models for GeoAI, and then I look ahead into the future. I was chair of the CSE department, my department, for 2 years through July 2023, and so my research really kind of slowed up at that during that time, I'm only kind of emerging from those administrative duties. And so I'm actually playing catch up with what is happening with foundation models and hope to make so that's at the moment why I'm focusing on other people's work, but I hope to now get back to research and make some contributions. Okay, so what is GeoAI and why should we care? So, probably don't need to say this. Geospatial artificial intelligence is broadly the application of AI methods to geospatial data, and it's mostly the application of machine learning, not so much the broader other aspects of AI. Most of it is machine learning. And geospatial, what is geospatial data, right? There's a lot of form of geospatial data. Why is it important? Well, it tells us about the Earth, right? It allows us to learn about the Earth. And these are perhaps obvious things, but just trying to provide some context. It's often said, and no one can trace back to find where this actually originated, but it's often said that 80% of all data has a spatial or geospatial component. This statistic is used, but again, where proof of that, or how would you prove that? But anyway, there's a lot of data related to location. So some examples, this will not at all be exhaustive. Obviously, some of the earlier examples are remote sensed imagery, right? From satellite images, aerial images. The idea is we know the location of where the image was taken. We know what's in the image. We know what's on the ground. Very simple paradigm, but very kind of powerful. And actually, most of my work has been in remote sensed satellite image analysis and computer vision. But then, of course, we have lots of other geospatial data, measurements such as weather, obviously things like maps, trajectories, where people are moving, where things are moving, survey data like the US Census, and, so geospatial data it can be, very broadly any data that can be associated with a geographic location. Okay, so I'll put this slide up, somewhat timely if you want to learn more about kind of the state of the art in GeoAI. There's just recently been a handbook published late 2023. It's broken down into, see if I can get my pointer to work here. Okay, it's broken down into kind of some introductory chapters to set the scope of the work, methods down here, and then applications, and then with some kind of looking ahead type things. So this is a kind of a good one-stop shop of contributed chapters about the state of the art in GeoAI that you could, if you want to learn either more, again, about methods or about applications, it's a good place to go. Okay, so let's look at the problem, the domain, GeoAI, right? So on the right here, we have fundamental AI, ML, DS. On the left, we have a domain, right? So this is a very kind of common situation. And the domain happens, for my work, mostly is on geospatial data. So one way that these two realms interact is, obviously applying fundamental AI, ML, data science applications to, or fundamentals to an application domain. And sort of, so you could, kind of blankly apply them, or you can think about trying to make some adaptation. And there's some interesting problems there in things that come up there with the idea of how do you adapt. And also these domains like geospatial data analysis hopefully can provide motivating problems for new research in fundamental AI, ML, and DS. But let's focus on kind of geospatial data. So some of the questions that I've asked myself and people working in GeoAI is kind of what is special about geospatial data, right? And particularly when we want to adapt these methods, what can we, what does it mean to adapt them to geospatial data? And are there aspects of data that can be exploited? And these are kind of my two themes, which I'll introduce in my next slide, are kind of related to these questions. How do we best adapt general methods to geospatial data? And is there some aspects, things about geospatial data that can be exploited? Okay, so looking back a lot of my work in GeoAI the last 25 years has been guided by two themes. One is related to how to make, adapting AI methods, ML methods, probably more precisely, to geospatial data, how to make them more explicitly aware, more spatially explicit, more spatially aware, more spatially knowledgeable. These are somewhat vague terms, but hopefully we'll see some examples, right? So kind of how do you potentially incorporate geographic laws, patterns, rules into AI methods? The second one is kind of a very simple paradigm, but one that I found to be very useful, is the idea that geographic location allows you to tie together lots of different types of information, right? And so I'll provide some examples of this in my subsequent slides, but this allows us to, associate different modes of data, perhaps images and text, satellite image and textual descriptions of a place. So you can tie these things, so there's kind of in the sense of a database key, being able to tie different types of data together. And one place where I think that becomes particularly relevant is in coming up with weakly supervised or unsupervised methods for training large models. And I'll elaborate on that later. The other thing here, this idea of geographic location as a key, is even if something is not meant to be geographic data, if it has a location, if you can associate it with a location, perhaps you can interpret it as geographic data or exploit it to learn to gain geographic knowledge. And I'll provide examples of this. Okay, so in the next couple of slides, I'm going to go very quickly through some work I've done on these two themes over the years. And again, it's going to be at a very high level, but give some examples of work in these two themes. Okay, so here, and the next, so many slides at the top, I'll provide the reference and then just say something a little bit about it. So back in 2003, while I was a PhD student, looked into using association rules for mining spatial patterns or spatial. So I don't know if people remember back to association rules, if they're still used. So they were in data mining for finding things like, if people go shopping, what types of products do they typically buy together to inform where to place products in a store? Or for a sports team, which kind of pairs or triples of players on the floor end up doing well. So finding these associations. And so we kind of asked the question, well, how can we adapt this to perhaps finding hopefully unknown or non-obvious spatial relations between kind of what occurs on the surface of the Earth, right? So again, we used images to kind of understand what's on the surface of the Earth. And the first thing we needed to do, and again, I'm going to just go through these things very quickly, was to partition the image space and assign kind of discrete labels in terms of the types of land cover are at those locations. So we have labels. What are our associations? Our associations are spatial associations. Something occurs next to something, or something is in a particular direction of something else. Land cover classes having these particular spatial associations. At that point, we could just apply the machinery of association rule mining to try uncover. And again, this is going to, I'm not going to go into the details here, but on the far right are things like, if two land type, 12 and 17 appear next to each other, or a particular spatial arrangement, then land type 0 appears with a low confidence level, 0.095. So these are the types of things we discovered. Okay, so that's, again, and the idea here again is taking something which was non-spatial association rules and trying to apply it to spatial data by coming up with these associations based upon spatial relations. Okay, so move forward a little bit. Around 2011, This is right before CNNs kind of overtook computer vision, and a lot of object analysis or image classification was based on these so-called bag of visual words. What are bag of visual words? If we look at these images down the bottom, was the idea of finding salient regions in the image, which are the yellow boxes indicate the kind of the salient regions of an image, and a descriptor, a vector describing what things look like there. So rather than having a descriptor that describes the entire image globally, you try to do some local analysis based upon you focus locally based on these salient regions. So there's been a lot of work on just using, and the bag of visual words comes from text analysis, where you would consider a document just as a bag of words. Again, we need to have the concept of words now that we're working in images. And so there was a way of quantizing or clustering, labeling these salient regions with a discrete label. Okay, so at that point, we can think about an image as being a bag of visual words, but that doesn't take into account the spatial arrangement of these visual words. That idea of just looking at the occurrence of the number of different types of visual words that appear in an image worked well for the image classification and object recognition. But we thought, okay, these are spatial images. Maybe the spatial arrangement of these bag of visual words is important and can be used to tell apart different types of image land cover classes. Okay, so again, we took something in the bag of and said, okay, let's try have a representation which goes beyond just counting the number of times certain visual words appear in an image, but what are their spatial relationships? So we came up with something called visual word co-occurrence matrix, and we looked at different predicates like being close to each other, having certain relative orientation, and incorporating it in. And this is there's a lot of details here. And once we had, we incorporated this co-occurrence matrix into a kernel, spatial pyramid co-occurrence kernel, which we could then use and support vector machine classification. Okay, and so again, the image, top in the top middle, and then showing the visual words, bottom right. I'm not going to go into detail here, but this is basically saying how for two visual words, we can either figure out whether they're within a certain distance or whether they have a certain relative orientation. Visual words, one of the things is they have an orientation. And so we would look at the orientation, relative orientations, and incorporate that into kind of the descriptor of an image. And the motivation here was to be able to tell apart things which are visually quite similar, but perhaps it's the spatial arrangement of these different density of residential buildings, medium density or dense, and to do better at telling these apart, classifying them versus something which does not incorporate the spatial relationship of the visual words, right? So we showed improvement on a 21 class land use classification problem. And what's kind of interesting here, and I didn't have this back in my first slide on the relation between kind of fundamental machine learning and a domain, but here we developed this framework for satellite images, but actually showed that by incorporating the spatial relationship of the visual words, we could actually do better than the state of the art on standard image databases like objects, distinguishing bicycles from cars and so on. So this was a situation where a technique developed in the geospatial domain actually helped the performance of a technique more generally. Okay, so third work here, a little more recent, 2021. So again, this theme of how do we make standard machine learning and methods more kind of spatially aware, more spatially explicit. So we looked at the cooling layer of CNNs, right? So since about 2010, 11, CNNs have been, well, up until transformers, for a long time, they were the dominant technique for doing image understanding, image classification, segmentation, and so on. So what we said, and again, I'm going to keep things at a very high level here, as opposed to this, and I'm kind of assuming that this will make sense if you're familiar with the pooling, what is meant by pooling in CNNs. But in the I'll maybe go down here in the pipeline of a CNN, there are stages at which you reduce the size of your representation spatially, and you do that by for a certain region in one of these feature maps. Usually, the most common approach is to take the maximum value to represent this region as you downsize your feature map. And we said, well, is there some sort of spatial structure we can exploit in the distribution in this window to select perhaps a better candidate to represent this when we downsize? And so there was something from geospatial analysis called Gettys-Ord GI star hotspot analysis, which is kind of a clustering technique, but it's not simply clustering. It's looking for kind of regions, this again is applied for geographic data, regions that are kind of in some ways significant, a group of places where values kind of are spatially clustered and different from other places in your region. And so we replaced the max pooling in a fully connected convolutional neural network for segmentation with our proposed pooling, and showed that it did better for the problem of semantic segmentation. The problem of semantic segmentation, given an image, segment regions, and the semantic part is assign them a label. And again, I'm not going to go into the details here, but we showed for this problem on standard data sets, our proposed pooling worked better than standard pooling methods. Okay, so let's change gears a little bit here and move to my second theme. Okay, so geolocation is a key for associating data. So I'm going to give kind of two examples of this. One, initially, I'll talk about how, and I mentioned this before, location allows you to tie together different types of information, and maybe this can be used for doing unsupervised or weakly supervised training of models. And then later on, in the second part of this theme, I'll talk about how we can exploit things that are perhaps not meant for geographic discovery, but since they have location, we can see if they're geographically informative. Okay, so first, what I'll do before going, I'll come back to that slide. But back in, this work was actually started while I was a PhD student in the early 2000s. There's something called a gazetteer. So what's a gazetteer? Gazetteer is kind of a dictionary of what is where on the surface of the earth. So a gazetteer would list something like all the high schools in California, or all, I don't know if it's exhaustive, but things like churches in California, right? So things and the location, it would have the location. Now, gazetteers were deficient in that the location, all they had was a single point, a longitude, latitude point, just because that the actual spatial extent or boundary of these objects was not available. So I kind of thought about this and said, well, okay, it'd be great if, first I checked with my geographers friends and I said, would it be better in these gazetteers if you had a bounding box instead of a point to represent these things, right? And they said, of course. Okay, great. So how do we come up with the boundary? This is kind of a segmentation problem. How do we come up with the boundary of these regions, right? And they are, you can kind of see they're visually distinctive. But now if we want to train a model that can detect, say, where high schools are or where golf courses are, we need training examples, right? In the usual supervised learning paradigm. Well, rather than have someone go and label, 1,000 high schools with the bounding box or the precise boundary, that said, well, we know the current gazetteers tell us that at this point, and hopefully that point falls inside the high school, there's something around that which is high school-like. And so the idea is, again, this idea of using location, in this case, location, as a way to get at, not the labeled high school precise boundaries, but to get a lot of examples of things that are high school-like, or at least the assumption is around that point they're high school-like. So what I'll do is come back to this slide now. So the kind of the bigger picture here, we have image data that we want to analyze. We have non-image data. The example I gave was gazetteers. Perhaps if we have 1,000 or 10,000 points, and we know around that is something that looks like a high school, we can use that weakly labeled data to train appearance models, and in a weakly supervised or in kind of an unsupervised way, perhaps to learn an appearance model that can then detect what high schools are, detect new high schools, or also in a feedback loop here for the existing entries in the gazetteer, we can go back to those point locations, use our model and say, what is the bounding box now of that high school there? And then update the gazetteer, okay? So here's kind of a result from that work where these are the kind of the regions that were automatic. Once we learned our appearance model, these are the regions that were classified as being high school. And again, this is not a precise semantic segmentation. We're not looking for the exact boundary, but at least the argument was we can get this automatically, and it's better than having a single point to represent the spatial where that high school is, right? And so kind of examples here, again, I won't spend too much detail. The yellow is the kind of a more precise ground truth. The red, boxes which might be hard to see, is what our kind of automatic, weakly supervised or unsupervised model was able to detect. And so that was that work. So the idea there of using location, well, I mean, it's kind of obvious, using location to tie together locations in an image with entries in a gazetteer. Okay, second is a series of works where I use this idea that if we have some data, it has location information, but perhaps that data was not meant for geographic knowledge discovery, perhaps we can still exploit it in that way. Okay, so that's kind of the framework. And so in 2010, my PhD students and I looked at the idea, what if we use ground level photos for geographic knowledge discovery, right? So obviously satellite images, aerial images have been used for a long time to know what's on the surface of the Earth. What about all the images that people are starting to take with cell phones, smartphones, and have GPS tags, right? And what can be gained from this that you couldn't get from a satellite image, right? So it's a ground level perspective. It's a different perspective, and also you can have photographs indoors, right, as opposed to what is from a satellite viewpoint. So leveraging kind of what had been done in general image understanding, can we apply that to large collections of georeferenced ground level photos, and learn something that we couldn't get from another source. So first we did a kind of so again, the context here, these photos are not necessarily captured with geographic knowledge discovery in mind. So they're a form of VGI, volunteer geographic information, because they're provided by non-experts. And they're serendipitous because the intent usually wasn't for geographic knowledge discovery. And they provide, as I mentioned, an alternate perspective to overhead imagery. Okay, so first we did a proof of concept is there was a task which you could use satellite images for. The task was to distinguish between built up and rural areas, right? And of course, that's something you can use satellite images to do. But we wanted to see as a proof of concept, could we use ground level images to do this? And another reason we focused on this problem is we had ground truth. We knew where there were built up areas and not built up areas. And then again, the motivation for why we might be able to do this is if we look at these photographs, Flickr images from the south of England, visually we can look at those and say, yeah, these represent, these make sense as the ones that are in London. It's a built up area. These ones that are more rural, they look more rural, right? Can we come up with a classification at the per image level and then use that to create a map, right? And so here, again, I'm just going to show kind of the results. the bottom left is the ground truth, the binary ground truth. White is built up, that's London. Black is other areas. And on the right are two examples of us using this paradigm of labeling individual images, taking some sort of a count within a region and deciding whether that 1 kilometer square is built up or not, right? And I won't go into too much of the difference between these Flickr images. Again, were images that anyone uploaded. These geograph images was actually a project that tasked people with taking geographically representative ground level images. Little variations, some data sets there. Okay, so then we took this paradigm kind of further. This is another work here. So now we said, well, okay, we know we can map built up and rural areas. What about mapping scenicness, right? So we started to kind of push this paradigm. And there's a website called Scenic or Not, where people rate ground level images as the level of scenicness. So we got a training data set of images, ground level images, scenicness values from 1 to 10 that people had assigned. We used that to train a kind of a regression image analysis regressor that, given an image, would output a value from 1 to 10, and then applied this to a large number of ground level images and see if we can map different ways of mapping scenicness, right? A heat map. And so we got some results here. One of the challenges here that, unlike the previous problem, we have no ground truth, right? So there's no way for us to kind of determine how well our technique is working. Okay, so kind of continuing with this theme, another paper, right? This kind of gets back to the idea that ground level images can often be inside buildings. So you can, a building might look the same at a hospital, and a shopping center might look the same from above. But if you were to have images or perhaps videos inside, perhaps you can tell apart their land use, right? And so we use this kind of framework to map land use. What we did is used university campuses because we kind of had the ground truth in terms of we knew what the campus map, we knew what different buildings were used for. And so, and again, some examples here, and you can, look at these images, and by looking at these images, we understand what's going on in them. We understand what that location is used for. And so, so we did this. I think on the left is the ground truth. I think this is the Stanford campus. And then on the right are two iterations of, again, us using just the ground level images that are located in these buildings or these regions to assign a land use. Okay, so perhaps a little further out there. And again, I'll kind of preface this, one of the benefits of being in academia, and I think faculty don't take advantage of this enough, is we can kind of look at things which they don't, can just for the kind of, we can be a little more risky, right? And so some of the work I've done on this problem is, well, why would you want to do that? Well, I'm obviously not going to, it's not going to become a product. I'm not saying it's going to work perfectly, but let's play around a little bit, right? Especially once I had tenure, as long as I keep teaching, bringing in research money and publishing, I can kind of look at whatever problems I want to look at or my students want to look at, right? So again, taking this paradigm, someone else had done work on given an image, assign an emotion to it, anger, fear, sadness. What if we use this to map these emotions, right? And so again, we didn't develop that. I'm not saying that is a great, makes sense to even do that because these are very ambiguous, but the module was out there. Let's see what happens, right? And so we could then make maps of San Francisco where there were, and we did some kind of hotspot analysis, some geographic analysis here. We see, and again, maybe we're not, nothing new is coming out of this, but we would see joy in Golden Gate Park and the opposite down in downtown, right? And at the ballparks, right? So it seems to be working, right? And then we could also, since we had time, we had multiple images over time at a particular location. We could look at a temporal domain and say kind of where is joy emerging so there's things in spatial temporal analysis, ways of detecting kind of emerging regions, and we kind of did that. Okay, so mapping human activity, right? So now we switch over to videos. So again, we took someone else's human activity video detector and said, let's apply it to a bunch of georeferenced ground level videos and see if we can map what's happening where, right? And so we actually had some undergraduates do this with pets too, which is kind of fun because, how do you know where pets are in the city, right? And people love to take photographs of pets. So it seems like a neat, and we kind of found some interesting things there. Okay, so that's the end of kind of my work. Now I'm going to switch over to kind of current work. That's the past, at least for my work. Let's switch over to the present, which again is not my work. I'm coming up to speed on it. And we're going to look at work on foundation models for GeoAI. And I'm not an expert on foundation models, but hopefully what I will say here won't be too far from kind of what they are, and for people that know more about them than me. But hopefully I'll be able to show you kind of what does it mean in terms for GeoAI, some interesting findings, recent findings, which I'm pretty kind of amazed by. So foundation models. So how, going back to this idea of these general machine learning or fundamental machine learning or AI methods, how spatially explicit, aware, or knowledgeable are they, right? Kind of out of the box. What if we do nothing additional to them? How well do they work for geospatial data analysis? And if they don't, are there ways to improve them, right? Making them better, and through the common thing of prompt engineering, or perhaps fine-tuning on a small labeled data set. Okay, so we're going to look at some examples of these two things in the context of foundation models. Very recent work. Okay, so a little refresher here, and again, I'm not an expert. The idea of foundation models is kind of, a machine learning model that can do lots of tasks, right? So it's a foundation. You're not designing a machine learning model to do, question answering, but you're designing something that with some adaptation could be used for, question answering, but a multi-modal machine foundation model could also be used for labeling an image, right? And in order to make these so generalizable, you need to train on a lot of different types of data, right? And what's kind of not shown here, and this because there's a large amount of data, these are huge models with lots of parameters that you need to learn. This can't be done through standard labeled, supervised learning. You need to have some sort of unsupervised learning or weakly supervised learning task here. So this is really kind of not shown here, right? So, and again, I'm not, but so for, as a concrete example, right, the GPT models for OpenAI, the generative pre-trained transformers, right? Well, as much as we know about them, they're trained on a large corpus of internet data. And the task there, again, the very simple task, at least as I understand it, is given a document, say from the internet, given up to word n, predict what word n plus 1 is. Very simple task, unsupervised, because we know what n plus 1 word is, and how well the model does during training. You can use that to improve the model, provide some feedback, right? Now that, again, for me, from that simple training paradigm, what these foundation models, what the GPT models have been able to do is for me, pretty mind-blowing. But that's a whole kind of other discussion. So this kind of the work that I'll present asks the question, how, if something was not necessarily trained for a geospatial application, how well does it work? Perhaps we don't have to train our own models for geospatial anymore. We can just use these foundation models. And a lot of people are asking this question in different domains or different commercial applications, right? And aside here, kind of get back to this kind of what data, if we wanted to train something that was kind of more geo-aware, what type of data would we put in here besides what we see here? And what kinds, kind of more importantly, what kinds of tasks would we use to train it? And especially in an unsupervised or weakly supervised or semi-supervised way. Okay, some examples. And again, I'm not expert here. This is not exhaustive, but there's different types of these foundation models. Perhaps one that people are most familiar with is the GPT, but now there's also from Meta, and I'm not putting Google in here. There's ones that are purely visual, right? This is for image generation, and more recently, the ones that are multimodal. So like GPT-4, where it can take as input either images, text, or both, right? Okay, so some work here by, so let me kind of back up. So on the final chapter of that handbook on GeoAI, I was asked to, again, this was a challenge for me because I've been kind of out of the loop a little bit on recent developments, but I was asked to look to the forward thinking on GeoAI, right? And so I framed this chapter around this question of how long is the coast of Italy, right? So if I asked someone, how long is the coast of Italy? What would the answer be, right? What would you expect it to be, right? And this kind of shows. So Google says this, right? This was back in October or so of 2023. Bing says this, right? So if you ask a geographer, is this a good answer? They'll say no, right? Because it depends on the scale, right? The length of a coast is a coastline paradox. It depends on, what detail, it's fractal at some level, right? And so these are useful answers, right? But these, really, this is not, from a geographic perspective, really not the correct answer. And I thought for sure, if I put this prompt into GPT, it would do the same thing, right? And lo and behold, we get back, right? This actually, it's aware of the coastline paradigm, right? Depending on the level of detail, right? And this, to me, was kind of, again, this thing that's been trained on just predicting the next word from the large collections of documents from the internet, came back with this. Now, whether it is, still you can ask the question, does it really know about the coastline paradox? At least it's kind of, it's not, its answer recognizes it. Okay, so someone else's work here, right? So recent work, 2023, some colleagues who looked at, opportunities and challenges of foundation models for GeoAI, right? Just as I was saying. So how well do these foundation models compared with things that have been specifically designed to do various geospatial tasks? And they looked at a couple things here, which I'll go to kind of show examples of. So toponym, so this is a text recognition problem. And toponym is a place name. So given some text, can you recognize all the place names in there? And then progressively kind of moving more towards not just text, but multimodal data. Well, here we get time series. So not just text, but time series. Here we'll start to see images start to come in, and finally remote sensed image. So a range of tasks, and we'll see the takeaway statement here is that these kind of already kind of trained foundation models can do well on some of these tasks at the top and less well on the bottom. Okay. Anyway, let's kind of look at how they discovered this, right? So, or demonstrated this. So geospatial semantics, so toponym recognition, right? So the idea here is taking GPT-3, feeding it in, giving it some examples of what you want it to do, right? An example of a paragraph, here's the prompt, and here's what the answer should be, right? So a couple of examples, then asking it, now, without saying, okay, what now actually do the task on some new text, and it recognizes the toponyms, right? And actually it does better than models that have been trained specifically to do this, right? So this, again, is, there's some, in these foundation models, at least for this particular problem, it has learned, it's spatially knowledgeable. Okay, location description recognition related, but now not just a toponym, but actually a specific location, right? Similar task, all text base, and it does the foundation model do better. Okay, with some caveats there. Okay, so they work well at this problem. There is, what's called a few shot example. So we're not really training or fine tuning the model. We're giving it a couple of examples of what to do, and then it's able to do well. Okay, time series forecasting, right? Different problem. The idea here is given 20 or so years of deaths from dementia at a particular location, predict what it'll be in the next year, right? So a prediction problem. And compared kind of 8 GPT models with 2 baselines. Baselines are actually somewhat simple in the sense they're just analyzing this data as a time series to make a prediction and kind of find a couple things, So we see here an evolution of the foundation models where GPT-3 performed better than baselines GPT didn't, right? Then you start to ask, well, why is that the case, right? And again, since these are closed models, we don't know how they were trained. You can stipulate things like, well, maybe GPT-3 now actually saw some time series dementia data, right? And I won't go into this, but these are kind of some of the prompts that come back, and you can see with the GPT-2, it's really just predicting whatever was in the previous year, just replicating that, so catastrophically failing. Okay, so point of interest-based urban function classification. So the problem here is given a list of things that occur near a place, given a list of points of interest and their type near a place, can you say what type it is from these, how many are up here? 6. And so again, a little bit of, I think in this case, a one-shot prompt, and then do the task, right? And we'll actually do both 0-shot and 1-shot, and found out, so one task-specific methods outperform foundation models, and 1-shot performs 0-shot, outshot. So we're starting to see where methods designed specifically for this task are starting to outperform the foundation models. So here's moving over to purely an image problem. So given with the multimodal foundation models, you can do things like given an image, how quiet or noisy is that location? And so doing this with a large collection of these images and seeing how well kind of an out-of-the-box multimodal foundation model can do, see that they start to, the CNNs here, kind of traditional approach, AlexNet, ResNet, and so on, traditional image classification, outperform multimodal foundations, right? So we're starting to see a kind of a breakdown here. And then a final task, a standard task of classifying different satellite images into 30 different classes. And again, the foundation models, multimodal foundation models out of the, don't do as well as the CNNs, but then there's a widely varying performance amongst the foundation models. And the stipulation here is that some of these have seen satellite images in their training data set do better. Okay, so let's think, so that was kind of just out of the box. Let's think about prompt engineering and fine tuning to make these foundation models more spatially explicit, right? So another work here, and we're going to do 2 things here and people that are working with these kind of GPT models know that prompt engineering, what you ask them, is very important for how well they perform, and fine tuning possibly, fine tuning as well, right? So if we simply ask GPT 3.5 about a place, it knows a lot, right? And this again is still, somewhat amazing. It's generating this text 1 word at a time on the right? And it comes up with this. But can this be used to estimate things like population density, education level? So this paper looked at these different things here, and they looked at fine tuning the idea that, okay, take this foundation model, perhaps give it 1,000 examples of here's a location, and here's what the population density is there, some ground truth. Give it a limited number, 100 or 1,000, do a fine tuning step, which can be computationally done efficiently through something called QLoRa, and perhaps also in the sample task, estimate population density and location, right? So fine tune with different number of training samples, a limited amount of labeled data sets, so to speak. And first we see that even after it's fine tuned, if we just give coordinates, they perform poorly. So this is where so fine-tuning alone is not sufficient. This is where the prompt engineering is important to provide spatial context. And what is meant here, that instead of just providing the longitude, latitude, they do what's called reverse geocoding to come up with an address and index into OpenStreetMap through the API to get 10 nearby places. Now this becomes the entire prompt into the fine-tuned GPT-3, and now it works really well. Okay, So that significantly improves performance. So here's a situation where we're taking kind of standard GPT 3.5, doing some fine tuning, doing some prompt engineering, and you can improve its performance. But you don't have to go back and retrain the entire 3.5 model. Okay, so from this particular work, right? So the idea is language models possess substantial geospatial knowledge. They're compressions of all this, snapshot of the internet type thing, and that includes geospatial knowledge. But constructing the right prompt is key to extracting, and perhaps doing some fine tuning. Okay, quickly some work that I've started to do in foundation models. So a master's student problem of given a satellite image, generate a caption, right? So given an image like this, generate a caption. And there's techniques for doing this. And what he is asking is, can we use foundation models to improve the caption? So can we use them to do two things? Find similar images that already have captions. And now we have the captions generated using a traditional approach for this image. We have captions from our retrieval, where a foundation model has helped. And can we use a large language model to synthesize all those captions to produce a final caption? Okay. And so kind of the idea here is, given this image, this is what state-of-the-art captioning can do. Let's use a foundation model. It's image and text embeddings to retrieve these images. Now we have 4 captions. Can we use GPT to synthesize that? Okay, so some examples there and there, a master's level project. Project that I have going on in SF funded is post-disaster assessment of regions or buildings using ground level images, right? And other data too, information about the building type, when it was built, and that kind of so on. But if we just think about the image aspect of it. So either given a single image post-event, or given an image pre-event and post-event. So pre-event's at the bottom, post-event, and this is a hurricane event. So the, kind of one way to approach this problem is say, okay, let's, do the traditional computer vision thing of, let's get a bunch of label training data, train a CNN that can, or a vision transformer that can estimate damage, right? But let's see what happens if we just take these images and put them into GPT-4, right? And given just this image, and again, there's not much prompt engineering that's been done here. This could probably be improved. What damage is in this image, right? Pretty amazing what it comes back, right? And at least from my having worked in image analysis for so many years. What about 2 images, right? So now it actually starts to say, this is, we don't say, not even like these are 2 images at the same house at different times. It figures that out and starts to make, So the idea here is, and I think it's kind of a general, kind of a theme, is that, especially in computer vision and probably other areas too, how well do these kind of foundation models work, either out of the box or with some fine tuning or prompt engineering, that we don't really need to go back. We can just use them as a tool instead of having to, for every vision problem that comes up, kind of redo the training and everything. So I think that's kind of an interesting question, and certainly comes up in GeoAI. Okay, I'm going to 2 more slides, future opportunities and challenges in GeoAI. So opportunities, multi-modal GeoAI foundation models. Well, what beyond images and text, how do we incorporate things like trajectories and map and survey data and all that kind of stuff? And what are the tasks that we use, particularly for unsupervised pre-training, right? There has been done some work for foundation models for satellite images. So now, kind of similar to how you predict in text analysis, the pre-training task is predict how that worked. Now you mask a piece of the satellite image and have the model try predict that. But is there other kind of other training, unsupervised pre-training? And again, spatial location for me as a key for associating data. I could see where, again, the idea of held out data, you have, satellite image and ground level description, a bunch of pairs, you can automatically get that. And now the pre-training task for model is given a satellite image, generate the description on the ground, and you can use that to improve the model, right? Something I'm not touching on is a big work in what are called knowledge graphs, and can they be integrated with GeoAI foundation models? And kind of interesting, other spatial Turing tests, right, to determine whether models are spatially, explicit, aware, or knowledgeable, what would those consist of, right? And we kind of saw an example of that work that was doing things like asking, what is the token? Well, that's not very exciting, but what kind of tests would you do to determine whether a model is spatially explicit aware? And there's some people that have been working on that. Okay, some challenges, right? So the first two of these are not new. They've been around before kind of foundation models or generative models. Geographic bias, if you're using training data, you're going to have a lot more data in some locations than others. And so your model's likely to be biased to work better in certain locations or have other types of biases. Generalizations versus spatial heterogeneity, right? So on one hand, we want models that are able to generalize spatially, but we also know that things are not the same in different places. So how do you kind of deal with this? You want to have a model you don't want to have to retrain at a new location, ideally, but you want it to be able to somehow adapt to whatever it's doing for that location, to the uniqueness of that location. And then something that I'm calling generative geography, right? So these are generative models, and I could go on a long time about this, right? I think this is kind of one of the scariest things about kind of the most recent advances in AI. These are all generative models, right? They're hallucinating is a word that's used. Maybe that's a bit strong, but they're not retrieving back. At least they're not retrieving anything. They're not going back to. You can't. They're just generating things a word at a time, often, right? What does that mean in terms of geography, right? What is generative geography? Obviously, we could ask it to create a satellite image or a map, but that's kind of meaningless in the context of geography, right? So how do we deal with this idea of these being generative? What kind of guardrails do we put on them? How do we, So this is a broader, the generative aspect of these models is broader than just GeoAI, but I think it has, it will have particular implications in geography. Okay, so that's there. So that was a lot of material, high level, some themes in my work, some current work, which I think is kind of exciting in foundation models, and a little bit about looking forward, especially concerned about, from my perspective, of generative models.
Thank you. Any questions? Not yet.
When the problem is touched a little bit wider. But I'm like wondering how the or some extent that I take care of you. For example, I asked the model sort of like more in the question. I give you a coordinate and I say, tell me what you know about this location. But the model like kind of like summarize like okay. Like a recent events, for example, this area has been affected by it lately. Yeah. This area around it has been affected, or there is a little bit beyond what we can do.
Yeah, and so asking one of these models, given a location, so you're thinking more about like events that have happened there, or I think so. And again, what I'll have to say is I haven't played around with these models enough to know that. I think that's something I hope to do soon, is to start. But I think going back to this, I don't know if I can go back to this one example where it seems to show, given this location right here, right? So given this location in New York, it knows quite a bit about that, right?
It's see record okay. For example, if you like that at 6-7, you type and you can find it for the urgent all the way. So that's not necessarily processing test. It's more the editing that describes this location. Thinking a little bit more in the surveillance point of view, let's say that I have a certain region that is, like more isolated. I have, for example, from like doing some kind of like scouting or calling a national park or something like this. So that's not something that I can like very easily just like search in the internet. It would be something more like, well, I look at the satellite feed right now and then I can like make assessments based on this. But a little bit like more open. And then, for example, if I give a locality schema that tell the model, like tell me if there's something wrong with it.
Mhm. Yeah. So okay. So less about just things that could be retrieved. Yeah, I think so. There's two answers there, right? So I think one is perhaps using prompt engineering to get okay. I guess the meta question is right. Is that information in the model, right? So we think about these foundation models as being a compression of everything that they were trained on, right? So this kind of we don't know whether that information may or may not be in there, right? And so, so one way to try to find that out is, we know that things are going to, prompt engineering is very important, right? To get access to that information that's in there. So I think one thing would be exploring what are the right prompts to ask. But then you still, even, what if that, you don't know, whether that, is that in there or not, right? Is that information that you're looking in there or not, right? Was it, it can only be in there if it was exposed to it through whatever its training data was, right? But these training data corpuses are huge. Now, one thing they certainly lack is they're not very up to date, right? Because they're a snapshot, and I think these GPT models know nothing about after some cutoff, right? But let's not worry about the temporal thing. So I think I think these are kind of questions that people are going to start asking, right? If that information somehow was in all that data that it was trained with, and maybe not explicitly, right? Unusual, right? Is it in that model? I don't know.
And I think when it's just about temporal aspect, for example, in the example that you showed, that like you just like get to read it of the house, but it's able to like reason that like something happened a little bit. All of the situation have changed. I just like thought maybe you wouldn't be a lot of effort to do some kind of like monitoring, and like for example, you have like just a satellite flying national park, for example, like this, and then have a model that like you kind of like alert you automatically that if you have like vultures or like real time. And that is not necessarily all the data set that has been used to train the model, but the model, because it can extract pictures so easily, you might be able like to refine the model, realize that like there has some kind of like temporal event that's significant that should alert you. And that could be used for a variety of like the purposes. For example, if you have like a flash polluters, just like give you a alert immediately because satellites they're watching. You have like vultures entering the national park with your file. You have someone that suffered an accident, and then you have like a car out of the road or something like this where there's no cell phone reception. The model is gonna catch this kind of like more or less immediately, and it's all the beautiful like for a variety of applications. And I'm just like thinking if this already exists or it's something that like
well, so I guess kind of the way I kind of see your question is, should we design something that specifically does this, right? Takes in satellite images, you train it what it means, to or I think the paradigm that we're often going to be shifting to now is why design that computer vision module? Let's just use what these foundation models can do, right? And does it get us close enough to that? No matter what this is a task you're talking about, it kind of observation. So that's kind of where I kind of see your question framed, right? I think there's all these tasks that are kind of downstream of these foundation models, and the question is how much, for any one of those tasks, how well can we do with leveraging the foundation model versus what we used to do before, and go back and develop something specifically for that task, right?
I think the opportunity there to kind of like a more open and then in help desk, because of course you can like view the in like let's go from 1995 computer vision model that's going to be able to identify some key features that you want. But if you have like this level of generality, you can have some sort of system that you can like even no expert there, like say, okay, tell me if like there is some weather event happening today or something like that. And then you can like even like receive an answer in like literal language. Or I don't know, the model would likely be able to annotate the image automatically and like give you something that would be like a huge effort to view. In a classical
I mean,
computer vision.
to build this here, I just,
It would be like a huge effort if you just build a classical computer vision.
Yeah. You've tried. I mean, how do you get the training data? Right? I mean, that's what this problem. Like, how do I? So yeah, no, I think these things can be leveraged. Now, I think that's the thing I will say is the point that I ended with. It's generative. What does that mean? How much do you trust what that's because it's generative. It's in the current taking like something like GPT-4 now, the research that's being done is how do you constrain that, right, and not have trust in it. That's a whole other. But I think out of the box, you got to be careful about what it's okay to use one of these to generate a cookie recipe, right? It's fine. Your cookies don't taste good. What about people that are asking for medical diagnoses, right? And so I'm really scared about that. And I seem to be an outlier. I'm really scared about this generative thing. But
I think we're about like that, but it still could be used upon terms of like first common trouble like analyzing data for like huge space. The travel system.
Oh yeah. No. And you validate and verify. Yeah. No, as a retrieval type, right, or a focus. Of course. No, it depends on. No. If you were to use it, you'd have tons.
Yeah. It's only necessarily to like that. For neither something that the model like copy up the rescue planning. You don't have this, but like provide a lot.
Sure. Yeah. No, I again, I'm blown away from what these models can do. Kind of out of the box, right? Well, good.
We'll come up there.
Actually, I have negative, but so many of the questions I want to ask are candidates to especially the national security space. Biggest challenges while in the absence of arms control fine level help with monitor verification. But that led me to, can you build a panopticon? Because that's what you want, but also that how folks are.
So can you build a panopticon, and that means something that sees everything everywhere all the time, or something like that? What is it?
Yes.
I don't know. Yeah, I'm just kind of Well, I don't. I mean, so I mean, at least the way that the current models they have to be trained, right? And then that's like a cutoff, right? So they're not working in real time. I mean, well, okay, depends how you use them, right? In terms of feeding in an image and getting some text back, that's real time. But in terms of something which is, the way I understand it, like, you're going to freeze that model at some point on what it's trained on. So that's going to, temporarily, it's always going to be not up to date, right? Now, whether that, in terms of your general question, are we going to have something which can, so I don't know the answer. I mean, I think these models are incredibly powerful, right? Well, I would say powerful. They can do kind of amazing things, and I don't know the context. I was at Oak Ridge National Lab last summer for a GeoAI symposium, and there was someone there from he was from the government somewhere, right? And he was very concerned about these models and what they might mean in terms of countries having advantages, right? And he had met up, because he was so high up, and I'm forgetting a lot of stuff, but he met with the team, the engineering teams from OpenAI, Google and stuff, right? And he was like, they don't understand how this works, right? They understand how we build it. They can't explain why it's getting the performance that it is, right? And so it's kind of scary and maybe things have changed in the 6 months, but I still think there's this idea. There's so many questions we don't know, both in terms of why they work as well as they do, and what can they be used for, right? And the prompt engineering is so it's no longer, now my students want to, the research they do is what to feed into these things, right? It's no longer about training the model or new architecture. It's really kind of what do you feed in to see if that information is in there and to get it out. But I don't know, in terms of broadening what they're able to reason about, and I guess as part of it's the training data. But they would, they take a long time to train. They're not up to date. So in terms of for surveillance or monitoring or understanding what's happening right now, they might need to be used kind of more what I'm showing here, where you've kind of fixed the model, but you're still using it to find out something. Yeah, I don't know. Have you guys played around with them? See, I'm the same way, but I just I see stuff like this. And I don't know. I drank the Kool-Aid in some sense, that after so many years of incremental advances, and then this happens. But then it's kind of great, but it's also scary because it's all fictitious, right?
Our project.
But
How?
Yeah. No. Yeah, for sure. Yeah.
What I'm both and either I address this that then have here questions. They're really hard to answer questions.
Yeah, and I think the other part that the labs can play, and I kind of stress this to the people I was visiting at Oak Ridge, is that industry right now has the monopoly on these because they have the compute power. In academia, I can't do research on developing these things, right? I have a couple of GPUs, right? So I think places like Oak Ridge and Livermore, but especially Oak Ridge, has the machines, right? And if we want to open up those machines or start developing, well, the context was GeoAI. Let's start thinking about developing and training GeoAI foundation models. But we need someone, Google's not going to do that for us. That's where the lab can play a role. It's providing those resources. Frontier stuff. Yeah, I don't know. And I just, as I say, after a hiatus from having been department chair, I'm kind of playing catch up a bit now. So I need to pay for my $40 ChatGPT for subscription and start playing around when I get time. Of course, now there's the $40 or $20, maybe the $20 at ChatGPT. Now there's $20 for Google's Gemini, right, per month. So it's going to be like streaming services, right? We're going to be paying $20 to each service.
Okay, thank you all for coming. We are closing the seminar now. Thank you.